What's up guys, this is Red Dust Tech. So basically today I'm going to do a different style of video. I'm going to do a podcast about assembly language. Or basically inline everything about assembly language at a level. It's going to be like 1 hour long, so it's kind of different from the usual style, but let's try it out. There exist several manufacturers of microprocessors, all in competition with each other. Two of which are Intel, which produce a range of microprocessors standard in most IBM computers, and PC compatibles, and Motorola, which produces a range of microprocessors used at the heart of Apple's MacBook. The major problem with these microprocessors is that they are incompatible with each other. Each family of microprocessors attempts to be downwards compatible with the same family of microprocessors. Example, Intel's range 8086-88, such that any software that runs on the earlier microprocessors is supposed to run on all versions on the later processors. This also results in disadvantages because for this to be possible, the latest version of microprocessor will probably do some things in ways that may not make the best use of current technology. Although each processor has a unique internal architecture, all have common principles which can be used to understand the microprocessors systems in general. They all have an instruction set, register. Nowadays, processors have more of these, and their size is becoming bigger. 64, 128, 156 bits. External buses. External address bus determines the maximum address space. Internal data bus determines the speed in which data can be transferred to or from memory. Internal buses, often a large size to facilitate super fast data transfer speeds. Note for the registers. General purpose register, the AX, accumulator, BX, BH and BL, base index, CX and CHCL, counter, the CX is counter, DX is data. Registers. These registers can be treated as 4 16-bit registers or as 8 8-bit registers and are referred to as EAX, EBX, ECX and EDX if they are 32-bit registers, where E stands for extended. CS, DS, SS, ES are known as segment registers and contain the address of the starting segment of the code segment, data segment, stack segment, and extra segment, respectively. The latter is used to manipulate strings. S1 and D1 are the source index from where and the destination index to where, respectively. S1, source index, is relative to destination index, and D1 is relative to DS. SI and DI, source index, which means from where, and destination index means to where, respectively. SI is relative to DS, and DI is relative to DS or ES. SP and BP are stack pointer and base pointer, relative to the SS. IP, instruction pointer, is relative to the CS. Flags or statues register stores outcome of arithmetic and logical operations. The CPU instruction set is the set of bit patterns that operate given machine. They are hence a set of operations that a particular machine can understand and execute. The instruction format consists of an opcode, which is the code of the operation to be performed, and may also consist of an operand, addressing information of the data or the data itself. The latter may vary in length. The number of bits allowed for the opcode determines the maximum possible number of operations in the machine instruction set. Example, an 8-bit opcode allows a maximum of 2 to the power of 8, which is 256 instructions. Programming in machine language is slow and difficult. Assembly languages were developed to simplify programming, still enabling the programmer to directly control the hardware. Note, assembly language was once widely used for all aspects of programming, but today it tends to be used more narrowly, primarily when direct hardware manipulation or unusual performance issues are involved. Typical applications are device drivers, low-level embedded systems, and real-time applications. These applications benefit by the increased speed in the processing assembler program instructions. Two main features of assembly languages are use of mnemonics and symbolic addressing. Mnemonic operation codes help make programs more readable, are easier to remember, are less prone to errors. Assembly language instructions are in one-to-one correspondence with machine language instructions. For example, for every assembly language instruction there exists a machine language instruction. Instead of using zeros and ones, a group of characters are used to denote a machine instruction. Different assemblers might use different mnemonic or syntax. Symbolic addressing. In machine language instructions, the address of data item or instruction is expressed as a number, binary or hexadecimal. This involves great tedium, especially when indexed or relative addressing is used or when the location of program in memory is not known. Assembly languages overcome this problem by the use of symbolic addresses. A symbolic address is a group of characters which represents the address of an instruction or data item. Example, add x num, where add is the mnemonic, ax is a symbol denoting the accumulator, and num is the symbolic address. In order to associate the symbolic address with the data item or instruction to which it refers, the address is first used to label the data item or instruction. Example, number DW defines a word and labels it number. Add x num. Num is now used as a symbolic address. The latter makes assembly language programs easier to write and more readable. Example, NMI DW, location storing a number. CMP AX NMI compares content of accumulator with data item at address NMI. BGE DWN branches to instruction labeled DWN if answer is greater or equal to 0 and 0 or Z is 1. Move MOV AX NMI load number at NMI into the accumulator. DWN PSH means down push AX. The above code snippet compares, means this code snippet I just said. The above code snippet compares a number in the accumulator with one address NMI and pushes the larger of these numbers onto the stack. Addressing mode. Many instructions require data to operate on operand. Meaning operand. The way by which an instruction refers to the required data item is called the addressing node. Different CPUs support different addressing modes, the most common of which are the following. Register addressing mode. In this mode, the operands of the instructions are in a register specified in the instruction itself. Example, move AX BX. Copy content of register BX to the accumulator. Inc AX increment means increment the context of the accumulator by 1. Relative addressing mode. Often using branch instructions to specify where the next instruction is located, relative to the current instruction whose address is held in the PC program counter. These instructions help program relocability. Example, jump plus 10, jump minus 10. Immediate addressing operand mode. In this mode, the operand or data is specified in the instruction itself and follows the opcode. Move AX #20 load. This means that load the accumulator with the value of 20. Add AX #27 adds 27 to the content of the accumulator. Push #65 means push value 65 on the stack. Unless the radius of the value being used is specified at the start of the assembly program, the data value is usually followed by D or an H, indicating the base of the number being used in the instruction. Direct or absolute addressing mode. In this mode, the address of the data item required is given by specifying its memory address. Example, increment count. Increments the contents of memory location labeled count. It was increment count by 1. Load AX50 stores the contents of memory location 50 in the accumulator. Move AX total. Move the content of memory location labeled total into the accumulator. Indirect addressing mode. In this mode, the address in the instruction locates the address of the data item and not the data item itself. This mode is most frequently used in jump instructions to perform what are called vectored jumps, where the address to jump to is contained in a given memory location specified in the jump instruction. Example, jump GMP 2000 does not mean jump to location 2000, but jump to address stored in location 2000. Thus, if location 2000 contains value 3000, such an instruction will transfer control to location 3000. Index addressing mode combines the value of a base register with that of an index register to provide the address of required operand or memory location. This mode is used a lot when accessing arrays. By changing the offset in the index register, different cells of the array can be accessed. Move S1 #4D. Move AL my data SI. My data, imagine a table. My data, there's like 1, my data, table 1, row 1 is 42, row 2 is 43, row 3 is 44, row 4 is 45. AL equals 45, because move AL my data S1. Example, move CX BX plus D1, which means combine the value of register BX with that of index register D1 to provide the address of the operand. Assembly language instruction format. A general form of an assembly language instruction has 4 parts expressed as follows: label field, opcode, mnemonic, operand, address field. Comment. General form of an assembly language instruction has 4 parts expressed as follows: label field, opcode, mnemonic, operand, address field, and comment. Example, start move AX BX. This is a comment. The label field is used to identify a data item or instruction and is optional. An opcode is compulsory and indicates the operation to be performed. Although operands are operational, most of the time they are present in an instruction. See note. Comments are optionally and are totally ignored when the code is assembled. The latter make a program more readable. 0 address instruction, example, halt, click, where no operand is required. 1 address instruction, example, push X, increment X. 2 address instructions, example, move X num. Instruction set. No matter which microprocessor is used, one can split up the instruction set into basic subsets, some of which are subroutine transfer instructions, stack handling instructions, compare and branch instructions, data transfer group, arithmetic and logic group, shift and rotate. Subroutine transfer instructions. There are 2 instructions in the group call and ret. The call instruction transfers control to a subroutine. The CPU executes the instruction in the subroutine until it meets a ret instruction, at which point the CPU continues executing the instruction followed by the call. Call and ret instructions go together. Following is an example of what happens when the CPU executes a call instruction in a program. Address instruction 2000, 2100, 5000. Ret call 2000. Initially, the program counter contains address 5000. CPU reads instruction of location 5000, call 2000 into the instruction register and increments program counter accordingly. CPU executes call 2000 by pushing the contents of the program counter on stack and copying the 1000 in the program counter. CPU continues executing instructions from location 2000 onwards until CPU encounters ret instruction. CPU executes ret instruction by popping value on a stack into the program counter and continues executing instructions from the location onwards. Although at first sight the call and ret mechanism may seem to be implemented by using two jump instructions, this cannot be done since the call instruction remembers the place where which it was called and always returns to the line following it, which is not a fixed address. Start. Call sub 1. From sub 1 goes to sub 1 proc. Call sub, then again it goes call sub 1 and it goes to sub 1 proc, and then ret goes to call sub 1 and ret goes to call sub. Back. Jump sub 1. Jump sub 1, question mark, sub 1, jump back. Stack handling instruction. Stack is a LIFO data structure, last in first out, in which the last item pushes in is the first item to be removed. Associated with the stack is a stack pointer, which is initially loaded with the address of the stack base and then keeps track of the position of the last item placed on the stack, top of stack. Two instructions that modify the stack are the push place item on stack and the pop retrieve item from stack. In both cases, the stack pointer is adjusted accordingly to always point to the top of the stack. Push AX pushes the contents of register AX onto the stack. Pop AX pops the topmost item and places data into the register AX. The stack grows upwards in memory from high to low memory location, and it organizes inwards 2 bytes at a time. Example, the SP is always incremented or decremented by 2. Push X, meaning SP equals SP minus 2. Pop AX is SP equals SP plus 2. Compare and branch instructions. For some time, instructions will be executed sequentially. However, there are many cases where instructions are needed to divert the flow on the program to different parts depending on the state of some particular condition. These instructions are used to branch or jump to a specified label or address to continue program execution from the label or address onwards. There exist different types of jump or branch instructions: unconditional and conditional jumps. Unconditional jumps transfer control to another part of the program unconditionally. Conditional jumps transfer control to another part of the program provided some condition is true or false. In these jumps, the flag register play a very important role in helping to decide if jumps are to take place or not. Example, JZ transfers control to a specific label if the result of previous operation is equal to 0. GNZ transfers control to a specified label if result of the previous operation is less or equal to 0. JE jump if equal. JNE jump if not equal. Some processors use branch instead of jump instructions. Jump instructions are often used with compare instructions. Example, the compare instructions compare two operands by subtracting the source from the destination operand and causes the flags to be altered. Example, CMP AX BX compares AX with BX and affects flags without changing the content of AX, unlike the sub instruction. Following is an example which combines conditional and unconditional jumps and illustrates the difference between sub and CMP instructions. Move CX AX keeps a copy of AX before modification. Sub AX BX AX equals AX minus BX. JZ make 1. If AX equals BX, then Z equals 1. Move DX hashtag 0. DX is equal to 0. Jump reset. Jump to restore to avoid next instruction. Make 1. Move DX hashtag 1. If AX is equal to BX, then DX is equal to 1. Reset. Move AX CX restores old value of AX, or jump AX BX JZ make 1. Move DX hashtag 0. Jump cont make DX hashtag 1. Continue. Data transfer groups. These instructions are responsible for transferring data between memory and the CPU registers, and between the CPU registers themselves. EX move AX20, move contents from location 20 in memory to register AX. The move instruction copies the value of the source operand into the destination operand without affecting the content of the source. Arithmetic and logic groups. Arithmetic groups. These instructions are used to perform arithmetic operations and usually include add, sub, neg, and CMP. Often include and decrement. All of them inc and dec, increment and decrement, are also included. Example, add AX BX, sub AX hashtag 20, inc with increment AX. The CMP instruction is similar to the sub instruction. However, unlike the latter, CMP does not store the result anywhere, but only affects the flags. Example, sub AX BX JZ label. By the end of the instruction, if AX was 10 and BX was also 10, AX would have value 0 and 0 flag would be set. Had the instruction been CMP AX BX and then skip a line GS label, with the value of AX and BX being the same as above, by the end of it, AX would still have value 10, and the 0 flag would also be set. There exist also different instructions for unsigned and signed numbers, example mults and MULU. The result of arithmetic instruction also affects the flag or status register. Z is 0 flag, indicates where the result of mathematical or logical operation was 0. C is the carry flag, indicates whether the result of an operation produced an answer greater than the number of available bits. This flag may also be set before a mathematical operation as an extra operand to certain instructions. N, and sometimes it says, is negative or sign flag, indicates whether the result of a mathematical operation is negative. V, sometimes O, is the overflow flag, indicates where the result of an operation has overflowed accordingly to the two complements representation, similar to the carry flag but for signed operations. I is the interrupt enable flag. Interrupts can be enabled or disabled by respectively setting or clearing this flag. P is a parity flag, which indicates whether the number of bits of the result is odd or even. In earlier CPUs, only integer arithmetic was supported. Later on, CPUs started having a floating point unit, also on the FPU, which could perform floating point arithmetic. In some cases, the FPU separate CPU called the math coprocessor, which nowadays is most often embedded in the processor itself. Pascal has an option and allows one to either use emulations done in software or 80x87, also known as use a coprocessor hardware, which allows double real. 80 times 86 PCs till 486 SX were without a MET coprocessor. The latter could be bought separately, called the 8087. Emulation could be done through which was slower from 486DX onwards. A MET coprocessor was included, meaning that standard, which is the standard in the CPU. When floating point operations are encountered, these are automatically sent to the MET coprocessor. Logical group. Logical operations include AND, OR, NOT, XOR, test. The latter all operates in bitwise mode. Example, each bit of a register is matched against the equivalent bit in another register when the operation is being carried out. This group of instructions also affect the bits in the flags or status register. NOT and or XOR leave result in register AX. Test AX BX is similar to the AND instruction, but the result is not stored in AX. Only the Z flag is affected. Masking is a chosen pattern of bits which either let a pattern of bits through a book, either lets a pattern of bits through or blocks it with either ones or zeros. This technique is used extensively to set or reset bits without altering patterns or other bits. If one needs to set a bit, one should, or it with should, or it with a. If one needs to reset a bit, one should end it with a 0. Example 1. Write assembly code instruction to obtain the two complements of a number held memory location labeled X. LDA, which is load X. This is what is written here. LDAX, not AX. This is like LDAX line 1, not AX line 2. Add #1, STAX. I would suggest using a paper and writing them while I'm saying them. LDAX is load X into the accumulator, not AX inverts all bits. Add #1 adds 1 to its content. STAX stores number back in X. Example 2. Write assembly code instructions to jump to label 1 if the contents of AX are equal to the contents of BX. XOR AX BX exclusive or the contents of the two registers. And then GZ label 1, lab 1, branch to label 1 if result is 0, in which case the Z flag would be set. Label 1, some instruction. Example 3. In a particular computer, characters are represented by an 8-bit pattern. The codes for capital letters are 01000001 for A to 01011010 for Z. And the code for lowercase letters are from 01100001 for A to 01111010 for Z. Give an 8-bit mask and the appropriate logic instruction, which will 1. Change any capital letter into its lowercase equivalent. 2. Change any lowercase letter into its capital equivalent. XOR. Number 1. Change any capital letter into its lowercase equivalent. And so this will come XOR 0010 0000 or OR AX #00100000. Now when it changes any lowercase letter into the capital equivalent, it will become same. There's a bracket XOR or and AX #110111. Example 4. Write assembly code instruction to check if the 6th bit of AX is a 1 or a 0, assuming that LSB is the 0th bit in register. Test AX #0100 000B or test AX #040H. I would suggest using a paper, writing these on paper. If Z flag is set, the 6th bit must have been a 0, otherwise a 1. Refer to example on letters book. On letter books, page 142, number 2. Shift and rotate group. Shift group. There exists two different sets of shift instruction. One set for doubling and halving unsigned numbers, SLH and SHR. One set for doubling and halving signed numbers, SAL and SAR. The instructions are very useful for dividing and multiplying numbers by a power of 2. Logical shift group. Logical shift instructions move each binary digit left or right and fill up the vacated spaces with zeros. The carry flag acts as a buffer to store the last bit which has fallen off the end. If during a left shift C equals 1, the shift has resulted in a number too big to fit in the register. If during a shift C equals 1, number just half was not even, and therefore the answer obtained is just an approximation. 2 is division by 2 is half, 3, 2 is half, it's going to be 1 and 1, so it's even. But if 3 is half, it's going to be 1.5, so it's an approximation. Example, SLH AL3, original AL 1010 result AL 0101 000, counter equals 1, C equals 1. SHR AL3, original AL 1010 result AL 001 0101, C equals 0. Arithmetic shift group. These shifts preserve the sign bit and make sure that this bit remains unchanged. The arithmetical left shift does not differ in any way to the logical shift. SAL equals SHL. Example, SAL AL2 multiplies AL by 4. Original AL 11111100 is equal to minus 4. Result AL equals 11110000 equals minus 16, where 0 fill vacated spaces. However, if while shifting bits left, the carry and the previous most significant bit are not the same, the overflow flag is set, implying that there was a change in the sign bit resulting in an error. In this case, C equals 1 does not necessarily mean that overflow has occurred as above. The arithmetic right shift shifts the content of the register to the right, leaving the sign bit unchanged. Before shifting, a copy of the sign bit is made, which is then used to fill the vacanted space after having shifted the bits right. Example, SAR AL2 divide AL by 4. Original AL 11111000, which is equal to minus 16, and the result AL 11111100, which is equal to minus 4, where sign bit is preserved. C equals 0. SAR AL3 divide AL by 8. Original AL is 11111100, which is minus 4. And the result of the AL is 111111, is equal to minus 4. This is division by 4. Base division by 4. Rotate instructions. When using rotate instructions, instead of bits falling off the end, the letter are directed around the path and redirected to the other end of the register. Rotation is usually done via the carry flag. One possible use of these instructions would be to test individual bits by bringing each bit successively into the most significant bit position, such as when performing log multiplication. Rotate left. Bills are rotated one bit placed to left, with the most significant bit value being placed in the least significant position. Example role BL1. Original BL 10110100. Result BL 011010001. C equals 1. Rotate right. Bits are rotated 1 bit placed to the right, with the least significant bit value being placed in the most significant position. The example ROR BL1, original BL 101101000. Result BL is 01011010. C equals 0. Using assembly language to express programming constructs. Loop construct. Pre-test loop, while do. Example in Pascal. While AX is less than 100 do, begin AX equals AX plus BX, BX equals BX plus 1, and end. Equivalently, in assembly, start CMP AX hashtag 100D, jump, stop, add AX BX, increment BX, jump, start, stop. Jump, which is written at GNB, stands for jump if not if not below 0. If subtractor of AX minus 100 gives a positive result, or 0, in which case n equals 0 or z equals 1. Post-test loop minus repeat until. Example in Pascal. Repeat AX equals AX minus 1. BX equals BX plus 1. CX equals AX minus BX until AX equals 0. Equivalent in assembly. Start decrement AX, increment BX, move CX hashtag 0D, add CX AX, subtract CX BX, CMP AX hashtag OD, GNZ start. Mid-test loop for to do. Example in Pascal. For I is equal to 3 to 25 do, begin AX equals AX plus BX, BX equals BX minus 1, and equivalent in assembly. Start move CNT hashtag 3D, CMP CNT hashtag 25D, J stop add AX BX decimal BX increment CNT jump start stop. J stands for jump if result above 0, n equals 0 and z equals 1. Multi-way branch. Switch if then else. Example in Pascal. If AX equals 0, then begin increment AX, DX equals DX plus AX, and else CX equals CX minus 23D. Equivalent in assembly. CMP AX hashtag OD, GNC actions underscore 2. Increment AX, add DX, AX, jump, done. This means subtract CX, hashtag 23D. Actions 2 done. Case contract, example in Pascal. Case AL of A, CL equals A. E, CL equals EI, CL equals I, O, CL equals O, C, U, CL equals U. And equivalent in assembly, CMPAL. J selection 1, J selection. Assembly language features and the way the assembler deals with them. Mnemonics is an easier and more readable way by which the opcode part of an instruction can be written. A table is kept storing each mnemonic operation code with its equivalent machine language operation code. This is possible since they exist in one-to-one correspondence. Each mnemonic operation code is looked up in the table, the corresponding machine language opcode placed in the machine language program. Symbolic addressing involves the use of labels to identify particular data items or instructions in a program. Label must be unique and must start with a letter and can then contain letters, numbers, and underscores. Spaces and punctuation marks are not allowed. During the assembling process, the address of each instruction or directive is determined. If an instruction has a label, then the address is associated with that label. A table is built of all labels used together with the addresses at which they occur. A symbolic address must occur only once in the program as a label if there exist identical labels at different addresses, an error is generated. The table relates each symbolic address to a machine address, most often relative to the start of the program, which is later changed to absolute when loaded for running. During the conversion from assembly to machine code, all labels are then replaced by appropriate addresses relative to the start of the program. Example, logical as indicated in the table. Automatic data conversion. If the value of data item is used in a machine language instruction, example, as an intermediate operand, then this value must be in the same notation as the rest of the machine language, namely binary or hexadecimal. In assembly language, the value of a data item can generally be expressed as decimal or hexadecimal, or binary number as set of characters. Example, low AX #16D loads this 60 into the accumulator. LOA AX or BC or inverted commas BC loads characters BC into the accumulator. Conversion algorithm and tables are usually used to change such representation into machine code format. Directives additional to assembly language instructions which correspond directly to the machine language to machine instructions set a particular computer assembly language have other instructions which operate at a slightly higher level known as directives or pseudo-code instructions. The latter have no counterpart in the machine language and greatly enhance the power of assembly language, making the computer easier to program at this level. These operations do not form part of actual program. They are not assembly language instructions but are instructions to the assembler. Example, AND indicates to the assembler when to stop assembling. Comment indicates to the assembler that what follows is a comment. DB indicates to the assembler to reserve a byte. DW indicates to the assembler to reserve a word. The assembler encounters a directive. It does not produce its counterpart in machine code but acts upon it as soon as it recognizes it. Comments. Anything appearing after a semicolon is comment to help make programs more readable. Only instructions to the left of the semicolon are obeyed by the processor. There exists also a method by which one can either comment about a program without having to precede each comment line with a semicolon. A set of actual comment is enclosed by the first non-blank character after a comment, pseudo instruction or directive, and the next occurrence of that character. Example, comment asterisk space asterisk. Simple macros. A macro is a simple instruction which represents a group of instructions. It is a block of text to which one assigns a name. It is defined at the start of the program by listing the set of instructions it represents. Whenever the macro instruction is used in the program, it represents the entire set of instructions previously defined. Thus, each time the assembler encounters the name of a macro in an assembly program, it replaces it by the actual block of text it represents. Unlike when using procedure, no call instructions are used to include a macro. Only its name is written down, and then code expansion is done during runtime. Hence, macros are similar to subroutines in that a program does not contain repeated occurrence of a group of instructions. However, no call and ret instructions are used with the former. Macros are preferred to subroutines since although they involve a longer executable code, they allow faster execution. Example, definition of a macro to increment a number in memory at address none. CNT macro MCD parameters define a macro instruction and name it CNT. LOA AX number, increment AX, STO AX number, ANDM, and macro definition. When the assembler encounters the definition of a macro instruction, it will decode the set of instructions and record the mnemonics of the macro instruction in the symbol table. When the macro name is then encountered in the body of the program, the set of instructions are inserted at the corresponding position in the machine language program. Macro instructions are expanded to the full set of instructions in the machine language program. The assembling process .asm, which means assembler.lst, and obj is linker.exe and map. ASM is the source code written in the assembly language. Assembler translates the source into object code, exists in various types, mainly 1 and 2 pass. .lst consists of the assembly language program. Its equivalent in hex and list of any errors detected in the program. .obj is the machine code equivalent of an assembly language program not yet in state that can be executed. Linker constructs an executable program by combining the entire object program into a single program. There might be a library of assembly language routines that can be used by other assembly language programs, such as a sort program. .exe is executable machine code ready to run. .map contains a list of starting and finishing addresses of the various programs segment relative to 0 initial location, unless otherwise specified by the user using the org directive. A debugger is a software tool that allows one to run machine code programs in such a way that one can observe the changes a program makes to register and memory. Some of these facilities it offers are the ability to display the content of all registers and or after the contents of a particular register, the ability to display the content of the flags register, the ability to enter values in memory, execute a particular set of instructions starting the IP and ending where it is indicated. List instructions contained in a given address and following the assembly language from chatter. The 2-pass assembler, basic assembler. First pass. 1. It breaks down the current assembly language program line into its consecutive part. Label, mnemonic, etc. 2. If the label field is not blank, the label and its corresponding machine address are stored in the symbolic address table. 3. The operation code is replaced by its equivalent machine language instruction, this address recorded. If the current assembly program line contains the value of date item in hexadecimal or decimal or as a set of American Standard Code characters, its equivalent in machine code is inserted into machine instruction. From the number of words used by the current instruction, the address of the next instruction is calculated. Second pass. If the current assembly program line contains a symbolic address, the letter is looked up in the symbol table and its equivalent machine code address recorded into the current machine code instruction. If the current assembly program line is the relative branch instruction, the relative offset is calculated and inserted into the current machine code instruction. Assemblers are usually written themselves in assembly language. They are not case sensitive and always perform static linking. Macro assembler. The type of assembler supports macros so that each time the macro is encountered within the source code, all necessary machine code instructions are generated. Meta-assembler is an assembler that can deal with different instruction sets. One can mix instruction sets into the same program. Cross-assembler is an assembler which is able to produce object code that will run on a different machine and run on different platforms. Note: API, Application Program Interface, calling OS function. Often there are many basic operations that need to be carried out, such as putting characters on screen, getting characters from the keyboard, opening, closing files, printing characters, etc. It would be inefficient if one had to write all these routines from scratch, especially if they are already used in the OS. These subroutines are usually executed by making use of interrupts to call a subroutine, and are usually called by name or number, not by specifying an absolute address. DOS produces a wide range of functions which can be brought into action by assembly language program. These functions work by allowing the programmer to interrupt the normal line-by-line execution of an assembly language program and branch into the OS's own machine code instruction. This is effected by calling the int instruction 256 interrupt and then specifying the required one. For example, move AH to 1 is function number 1. Int 21H needs to do it. Int gives access to a whole range of input or output functions, and specifying which one once involves putting a code number in register AH. There exists 256 software interrupts, 15 hardware interrupts, and 21 H gives access to this display screen and file handling routines. So that's it for assembly language. This is for intermediate. Now it's for A level. If you're stuck for this so far, God bless yourself. Don't forget to like and subscribe. Peace out.